Okay, hi everyone. So this is the third lecture, and we're going to try to squeeze a fourth one in this afternoon. For scheduling reasons, that's just the way it worked. So today we're just continuing. Last week we were looking at BPS solutions, and I mainly spoke about what I guess I called special holonomy manifolds. But normally that term refers to compact manifolds like a Calabi-Yau or a K3 or a spin 7 or something. But I slightly abused it by looking at non-compact examples like PP wave and this multi-taup nut, Gibbons-Hawking metric. But what's more typical in supergravity, of course those are universal to supergravity, but what's more distinctive of supergravity are the fact that you get these form fields. So in 11-dimensional supergravity, so everything I said so far was universal. We have a three-form C. So let's see if we can find solutions that carry charge with respect to this. And these will be, the first type of solution we'll talk about are so-called M2 branes. So I'll talk about branes more generally after we've constructed some examples. So this thing is roughly analogous to the A mu of electromagnetism. It's an abelian field. It's not non-abelian. If you can make it non-abelian, you'll be famous. But nobody thinks you can. Anyway. But it's a form field, so it's like a higher dimensional version of a Maxwell field. And its equations of motion are very similar to a Maxwell field. In particular, there's a gauge symmetry. Which is just delta C, in form language, is d lambda over 2 form. Or if you like, delta C mu nu lambda is d mu lambda nu lambda anti-symmetrized. The reason being, of course, that this means that dc is invariant. Now, there was a term in the action which was C wedge dc, but that's close enough. It's a Chern-Simons type term. It's still invariant locally under this. Up to a total derivative, that is to say. Okay, so M2 branes would be something that's going to be analogous to an electron. An electron carries a charge with respect to the A mu of electromagnetism. And the normal, of course, different gauges will do different things, but the natural thing to do to describe an electron would be to imagine that A0 was not zero. And you'd write you'd solve Maxwell's equations and you'd find something like A0 is 1 over R. So here we're going to imagine that C not 1, 2, I'm just going to call it C, is not 0. So this is going to split space-time. So we started off with R110, and it's going to now look more like R12 times R8, where this is not 1, 2, and this, which I will call, I think I call M, yeah. And this is IJ, which would be 3 to 10. So as soon as you turn on C, it makes that split. So the natural ansatz to try is something like this. Something that's going to preserve the splitting. E to the 2b. So here, A, B, and C are just going to be functions of the xi's. So we've got translational invariance along this three-plane. Yeah.
So can you explain again why the three-form was the split of the geometry?
Well, you started with 11 dimensions where all coordinates are equal, and now you've turned on C not 1, 2. It's not 0.
But
Right now I'm only turning on C. So I should say this is the only.
So you're only turning on the 0, 1, 2.
Yeah, sorry.
Oh, okay.
Yeah. A generic solution will bugger up everything, right? And there'll be no special directions. And yeah. This is saying, no, we're going to want, we turn on C0, 1, 2, that splits up into a plane and it's perpendicular plane, if you like. Of course, it's a 3-plane and that's an 8-plane. And then I'm still going to keep translational invariance along this direction. This is what's called the p-brane. I was going to first do these solutions and then motivate p-branes rather than the other way around. But it turns out this is the natural solution to do. So we're going to have translational invariance along 0, 1, 2, but not translational invariance in these directions because things have a non-trivial profile in that direction. So we get to do more vielbeins. Oh, you like my underlined colors, I guess. So what's the vielbein frame for this metric? An obvious choice is En, and I'll do my colors in a second. So that's going to be an obvious vielbein frame for this metric. Let's do this a little slowly for this one more time. So this is DEN, and actually it's helpful to write it this way. You don't have to write it this way, but it can be helpful to write everything in terms of the e's. And I put a bar here. Do you remember I spoke about this in week 1, I guess? So di bar is e I j d j and a bar. And this is the inverse vielbein. So this would be just sorry, yeah, this is right, sorry. E to the minus b d I. So this is an example, if you want to use this notation. And I think it's nice because it makes things more algebraic. So this is not really a derivative. It's a derivative times a function. Yeah. So that's why it won't commute. And then on the right-hand side here, I've done J, okay. I did a naughty. Okay, yeah, well that's right. Here I did it slightly differently. So let me just copy what I wrote. And again, I can write this as okay. So you need to find the spin connection components, and I'll just tell you what they are. So that works. So that's going to give you this guy, right? So remember what we want is, I'm used to writing with iPads now where you can just move things. So remember what we want is this is to be, well, I guess mu. And this has to be minus omega J mu. And then what I rubbed off, so the solution is and then I put okay, so hopefully you can sort of guess that this is a solution. Remember, I gave you a formula, which of course you are welcome to use, but this is a guess, and you can see it's going to work, right? So if I put in here and I wedge it with EI, so that's what it would tell me to do. I wedge with EI, I'm going to get precisely this. And the minus sign is because this is EI wedge EN, but this would give me EN wedge EI. Right? And the other component, we're just going to take to be 0. So that works. And then similarly over here, I have to wedge this well, first with EI. This term would be 0 because it's EI wedge EI, and then I just get EJ with EI, which is what I want, and then the DIB. And this term I had to have because of antisymmetry. And similarly, this term tells me that omega I upstairs n is not 0. In particular, it's proportional to E n. You'd have to lower the index. But that doesn't screw things up because when it comes in here, you wind up with En wedge En. So you can check that this is the good vielbein. Okay. So now our task is a little bit messy, but I thought I'd go through it at least in great detail for the M2. There's another solution we'll discuss, the M5, but I don't plan to do it in as much detail as I plan to do the M2, simply because of time and boredom. So, next. We want to look for supersymmetric solutions. So we're looking to solve delta psi mu equals, well, what is it? It's d mu. I haven't told you what it is yet, have I? I don't think I did. So in 11D supergravity, no surprise, the gravitino has a variation of d mu epsilon. That's like a free gravity, well, it's not a free theory, but that's the default thing for any supergravity. What you write on the right-hand side here is what sort of determines what else is in the theory, and it turns out to be this. 1 over 288. And again, this is not something that you can just pull off the top of your head from. So there's gamma mu nu lambda rho sigma, and then there's minus 8 delta mu nu gamma lambda rho sigma. And then what I'm going to call here is G nu lambda rho sigma. And C here, G is what's known as DC, and that is formally it's 4 times the derivative antisymmetrized. But for us, this just turns out to be minus epsilon MNP DIC. So that's the only non-zero component for us. It's the analog of F mu nu. It's the derivative of the gauge field. And then you have these somewhat nasty, but you'll see that they're not nasty, they're very nice. But they don't look very nice. Coefficients in front of the gammas. So that's the supersymmetry variation of 11D supergravity. So that's what we want to set equal to 0. Well, we've basically computed the first term, right? Because that's what you need this spin connection for. So let's write that down. dm epsilon would be this. That's the definition. Now I'm going to assume the first term is 0 because nothing's depending on the 0, 1, 2 coordinates. So all you're left with is the second term, and you just get a 1/2 dia, and now I've stick e to the a minus b gamma m I epsilon. That's just this. There's a factor of 2. It went from 1/4 to 1/2 because there's an ni and an in. So they add up. And then I went back and here I wrote it was di underlined, but now I've undone that because it's more useful now to write it as di normally. Yeah. And then that's why you get the e to the minus b, and the e to the a comes because en has an e to the a in it. Right? Are we okay with this?
Sorry, did you say you assumed that epsilon wasn't dependent?
Yes. So everything's going to be invariant under these directions. What we're actually imposing is Poincare invariance along, so translations and rotations and Lorentz transformations along 0, 1, 2. This is, I mean, at this stage we're just trying something naive. Of course there's a long story here. This is a p-brane, this is the M2 brane. But we'll discuss that after we found the solution.
So are you saying epsilon is localized to the internal space here? Or are you saying epsilon is being localized to the internal space?
Well, not
by hand, or?
I wouldn't say localized because of course it exists over the whole space-time. It's just that it's not a function of x0, x1, x2.
It's just a constant spin of the space.
Well, of course, the word constant spinner is loaded. That means d mu epsilon equals. It's constant, literally, yes. In this frame, in this choice of convention, in this choice of a frame, it's literally constant in 0, 1, 2. Yeah. Yeah. The name of the game in this story is to find a solution which does this, a solution to this. Once you find the first ones, and these were found by Gervin, I believe, back in the 1980s or even early 90s, and this will turn out to be half supersymmetric. You can find more, way, way more. I mean, ask George Papadopoulos, he will tell you. There's way more classification of solutions to this, but typically everything more than this will break more supersymmetry. So for example, this is going to be an M2 brane in the 0, 1, 2 plane. Of course, you could put the M2 brane in any plane you like. We just happen to be calling it 0, 1, 2. But then you can also have M2s in 0, 1, 2 and 0, 3, 4, and intersecting like that. And actually, you can have quite complicated arrangements of intersecting brane. Each time, epsilon becomes more complicated. And actually, well, and you lose more epsilons. It becomes more and more. Its components can become more and more projected out. But we haven't got there yet. So let's do di epsilon. So that now I'm not claiming the first term is 0. Okay. I shouldn't have used PQ there. I should have used nu lambda. You allow me to, well, I won't go back and change history. So this should really have been nu lambda. Meaning it ranges over the full 11 dimensions, not just the I didn't say what PQ are, but they look a lot like MN. And they weren't meant to be MN, they're meant to be new lambda. They range over the full 11-dimensional indices. Okay, what do we get here? Well, we're going to keep the first term. We don't have translational invariance in the xi coordinates, so there's no reason to assume that that derivative is 0. And then the next term, well, it comes from here. And again, you get a factor of 2 from each of the two terms. And I'm just going to put in what you get, dj b gamma ij epsilon. Right. That's okay. I think I can rub this off now. Now we have to struggle with this term. Here I would like some audience participation. How slowly do you want me to go? Or because there's a bit of bookkeeping to get this right, and I hope I got it right. The answer I got was right, so we can only hope. Okay, so the first term, we have m downstairs, nu1 to nu4, g nu1, nu2, nu3, nu4, epsilon. Any guesses as to what that's equal to by our ansatz? Remember audience participation Monday morning.
0.
Thank you. Yes, that's 0. Fortune on our first endeavor shines. Okay, now we put an I. Well, we get a factor of 4 because remember it's over here. The I is in one of the 4 slots, so you get a factor of 4. So that would make this, the way I've done it here, gamma I, and then the rest are m, n, p, j, g, m, n, p, j. Okay, and now we put in our ansatz. There's a minus sign, don't worry, it's just because there's a minus sign there. It's not important. Then it turns into a 4 factorial. Because there's 3 factorial ways to put the MNPs into the 0, 1, 2s. So this becomes minus 4 factorial e to the minus 3a, because remember, these gamma matrices are not in tangent frame, but now they are. Now I'm going to put them into tangent frame and do a little bit of manipulation. So now they are in tangent frame. You get e to the b here and an e to the minus b there, so they cancel off, and then there's e to the minus 3a from these ones. And then I got this. So I'm going to do one more thing. Actually, I'm going to do this. Another assumption that if you're in the business, you know to do it, but this is what somebody first figured out to do. You want to choose this projection. That's going to kill half the components of epsilon. Yeah, the plus or minus sign, and they did it downstairs. So at the end of the day, this becomes minus or plus, if I'm not mistaken. Oh yeah, there's a bit of I did one thing wrong here. You get there's a plus here, because you get a minus sign from taking this through 3 things. So this now becomes minus or plus 4 factorial e to the minus 3a gamma ij epsilon. And now we have to do the other one, gamma, okay, yeah, not the other 2. So those are the first 2 terms. Remember, we've got 2 different cases, mu equals m and mu equals I. So here and here, and here and here. This is the first term, and now I have to worry about the second term. delta m nu 1, gamma nu 2, nu 3, nu 4 what's that? Okay. Well, these are nu's, so there's 3 possible ways you can get the nu. So we'll write down a 3. There's a minus sign because of this fact that g is minus dc. So what you get here is epsilon m n p, gamma m n p I, d I c. Epsilon. Yeah? And then you just do a little more work like this. There's a 3 factorial, because basically there's epsilon contractions here. I'm sorry, there shouldn't be an m here, because the m is hanging on the left. So you get a factor of 2 factorial from these. And I'm going to put it in tangent frame. We see, look what I get, e to the 0, 1, 2. I'm using a bit of an identity here, which I'll explain in a second. That's right. Then I've got my e to the minus 2a minus b dic epsilon. What have I done here? I've used an identity, which is that gamma np epsilon is epsilon npq gamma q gamma 0, 1, 2 epsilon. Is that legible? Probably not. I've used a slight identity here. Let me write it more clearly. Gamma np equals epsilon np, and I guess let me do it all in tangent. Np q gamma 0, 1, 2. This follows from this projector up here. And let me just check the sign. How do I check the sign? I say, well, if this is 1, 2, then this is 1, 2, 0. So it becomes epsilon 1, 2, 0. Then that would be 0, gamma 0, 1, 2. So that's minus gamma 0, 1, 2. And I've got it upstairs, so that's, and that would be plus 1 for me. So actually I realize I have to get a minus sign. So we can use that identity, which means that I have to put a plus there. And then that's plus or minus 3 factorial gamma m. I meant to put the underline there. Oh. Okay. So this is a little tedious, I agree. We've got one more to go, which I was hoping to squeeze on this board. Let me try, because it's not as bad as the others. The last one we want is delta I, nu 1, gamma nu 2, nu 3, nu 4, g nu 1, nu 2, nu 3, nu 4. Well, here, you're just going to get a 3 factorial, because this has to be, it eats up the one I. Remember, G, where is it over here? G has one component an I and the rest are MNPs. So this tells you that you pick up the I, and the rest are MNPs, so it gives you the 3 factorial, and then it's just gamma naught 1, 2, and then di c epsilon. And by our logic, this turns out to be plus or minus 3 factorial. I'm wondering why. I think this looks like a sign mistake. Okay, let's just go with my notes before I. 1, 2, 3, e to the minus 3a di c epsilon. So I probably want this to be right. I think there should be a minus sign here. Yeah, and there's a minus sign there because c is minus. Okay. Is this too laborious? Well, we're done now, basically. So. But I wanted to do at least one case in its whole full glory. Yeah? So these are the formulas we've got. We have to solve this. We have to find all 3 terms in this equation when mu equals m and when mu equals I. Yeah. Yeah. Probably. Sorry. Yeah. Where?
Plus 3i.
Oh, here.
Where in the previous calculation?
This one? It's over here.
Yeah.
Oh, yeah. Where is it gone? It's there. So it's here. Yes. So thank you. We'll just put it in, and I've included it because that's why you got a minus b. So that's where. That's in the tangent frame. This is in the notes, obviously, because that's what I'm looking at. And I did check it carefully. So if you want to go through it quietly and convince, but I'm trying to show you how you would do it, and also a flavor of how it works. But obviously, it's a little too much to nail down in one go in a live lecture. So our next task is to solve this equation case by case. But now we know all the terms, so it's just a question of adding them up. So I can rub this off, but I want to keep these. Okay. Delta psi m 0 is equal to that. Well, we get 1/2 dia e to the a minus b gamma mi. And I'll put the epsilon in a second. That's the first term from here. Now I have to get the term from here. So there's going to be something over 288, this term, which is the top term up there. So actually, that gives me 0. That's nice. And then the next term will be plus 8 over 288. And that's this term here. So it's plus or minus 3 factorial. E to the minus 2a minus b gamma m gamma I. All times epsilon. Yeah. So you can factor things out, and this gives you a simple equation. dia e to the 3a, so I've multiplied through, so that e to the minus b's cancel off, but I multiplied through by e to the 2a, so I get dia e to the 3a, and then here, minus or plus, why do I get a minus or plus? This is plus, well, this is not an important sign, but let me just see why I'm disagreeing with my notes. I'm going to, in the interest of time, I'm going to stick to what I have in my notes, which is off by minus sign here. A bit worried, but because I probably did that a bit too quick. I think this, well, my notes say this is correct, but then when I stick it in here, it would give me a plus. Well, okay, let's go with what I seem to have, and I'll check my notes later. So, well, what's 3 factorial times 8? Yeah, 3 factorial times 8 is 48 times 2, isn't it? It's just 24 times 2, 48, sorry, you're right, 48. And then there's a half over here, so actually that gives me 96, right? And then this is DIC. Oh, I dropped that. There's a DIC here from over there. This number is also known as 1/3. You say they look like crazy numbers, and there's a 3 here. So at the end of the day, you find that the solution is just C equals, and I'm switching sign, but it doesn't matter. From my notes, I'll have to check that. C is e to the minus or plus e to the 3a. I do question this sign, but let's not dwell on it in the interest of lecture. Okay. Now I want to do, I guess I can rub this off, I don't need it anymore. The next one, which is 0 equals delta psi I. So now I have the full Monty, because I've got di epsilon hold on, what am I doing? Yeah, that's right. Got di epsilon here, and then I've got this term from here, minus 1/2 dj, that is b, gamma ij epsilon. And then I have the bits here, that term and this term. So the minus 1/288, and the first one is going to give me a minus 4 factorial, so plus 4 factorial, oh wait, minus or plus, so plus or minus 4 factorial, e to the minus 3a, is it? Yes, gamma ij epsilon. And then there must be a derivative djc. Okay, and then the last term, 1/288, there's a factor of 8, and the 3 factorial according to my notes, which is, yes, down here. E to the minus 3a again, and then that's it. Oh, there shouldn't have been a plus or minus here because that's what the gamma is doing. Yeah. So there's a plus or minus, which becomes minus or plus because of that. Oh no, that's fine. That's fine. Plus or minus. And then again, it's going to be, it's just DIC. Epsilon here. Okay. What you want to do here is you realize there's 2 types of terms. There's this term with the gamma ij, and the one over here, and this without. Triangles. 2 types of terms. Yeah?
So in the relationship between the C and the e to the 3a, that could be a constant term.
Yes. So,
you set it to 0?
right, so of course I could have added a constant to C, but it's only the derivative of C that appears in anything physical. So I just set it to 0. Yeah.
So it's like you reabsorb it in the gauge particle.
Yeah, if a constant C is gauge equivalent to no C. So adding it doesn't do anything. All right. The triangle terms, well, according to my notes, these triangle terms, triangle, will give you something like this, di epsilon, and I have to use what I had before for C, so this becomes minus plus 1 over 288. There's an 8 times 3 factorial, but then there's another factor of 3, because when I differentiate, I'm going to get a 3a there. And then this exponential kills that exponential. So again, this is differing by a minus sign from my notes, but this you can solve. Oh, first of all, these numbers again. This numbers I claim is simply, well, this is 48. We already decided times 3, so that's 144. So this is a half. Sorry, is it? So that's a half, and the solution is simply epsilon e to the 1/2 a times some constant epsilon. And let me just get the signs right. Well, according to my notes, it's minus a half. Oh, that, yeah, sorry. Here I put DIC, there's a minus or plus, and that should kill this plus or minus, so this gives minus. Again, I'm a bit worried about the sign, but it won't matter. Where this is constant. It's constant and it projects to this. Ugh. So this is where you have a non-trivial killing spinner. Nobody said it had to be constant, right? It's covariantly constant, but it's certainly not constant. You have this factor out front. And again, like I guess this is a minus sign between my notes and what I'm writing here, but it's not going to matter.
Isn't that 1 if 8 times 3 factorial times 3 over 2?
So this is 48. Isn't it?
Wasn't this 1/3?
But there's no, it wasn't that alone. There was a factor of 2 here.
Oh.
Yeah. The moral of the story is the 1 over 288 is not some random number. It is just so that enables this solution to happen. So this becomes a half. Of course, it wouldn't have mattered if this number was 16 over 22. You know, you just exponentiate what you get. And it's there. So that gets rid of the triangle terms. The square terms, well, you just want them to cancel. That's all. Again, you put this in, it's going to give you an e to the 3a, and that'll cancel the e to the minus 3a. So the exponentials go away, and you're just left with something like 1/2 djb. And here that sign's going to really matter, so I'm going to go with my notes. So I put this into there, I get a factor of 3. 3 times 4 factorial over 288. And there's a half out here. And then this is dja. But the question is, according to my notes, which is this is where it's important, so I'm going to go with my notes. you get a plus sign. So this is the equation you need to vanish. And 2 times 3 times 4 factorial is 12 times 4 factorial, 12 times 24. It turns out that this number is a half. So this tells me that B equals minus a half A. In other words, this is a quarter. Yeah, it's 48 again. So that's a quarter. Sorry, it's a two. All right. So I can rub this off now. So we have solved delta so that gave us what? I'll just write it down. C is plus or minus e to the 3a, or minus or plus or whatever, but minus or plus apparently. B is minus a half a, and our epsilon that's our solution. This isn't enough to solve the equations of motion, it turns out. I'm not going to go through the equations of motion because we haven't fixed. We found C as a function of A and B as a function of A and the epsilon is a function of A. But what's A? You have to do one more thing, which is use the equations of motion for the C field. And the equation of motion for the C field is d star C equals 0. The equation of motion is a little bit more complicated than that in general because of that C wedge DC term. But it's that C wedge DC is going to be 0 for us because C is so simple. Right? It's only in the 0, 1, 2 directions. So C wedge C is going to give you 0. And C wedge DC is going to be 0. So that part you can ignore. So you just have to work out this. Well, star D. So remember, our C is literally C3, we put an index on it, was C dx0, wedge dx1, wedge dx2. So dc is dic. I'll put a minus sign and I'll move this I through. Yeah. I'm going to do this fairly schematically because you don't need the details that much. If I take the dual of this, what am I going to get? Well, you have to have the determinant of the metric, which is 3a plus 8b. That's the square root of the determinant of the metric. There's going to be a 1 over 7 factorial because this is a 7 form. The dual of it is a 7 form. This is the minus sign, of course. Then I have to raise the metric. Well, the raising the metric gives me e to the minus 2a 3 times. And then, because of 0, 1, 2, e to the minus 2b once. And then I'm going to get dk, I guess I've still written it in terms of c. Yeah. And then, what is it? It's I need some more room. There's an epsilon, and it's going to be I1 to I7k. There's a k is here hitting the derivative, and then I've got my dx I1 wedge dx I7. So this is a 7 form, right? A 3 form, dualizes, d of it is a 4 form. We're dualizing it, so that turns it into an 11 minus 4 equals 7 form. And it's all pointing in the I direction. And it's epsilon I1 to I7 times k and a dk here. Alrighty. Well, what we want is the next step, which is d star dc3. If you think about it, this is now going to be an 8 form, right? 3, 4, 7 plus 1, 8 form. And it's going to live entirely in the transverse space. And the transverse space is 8-dimensional. So this transverse form is going to be something, and then just dx3 wedge all the way up to dx10. It's going to soak up all the I indices. And it's just a question of what goes here, and what goes here is just the following. It's some number, there's that dk, and then you have to add up what you get here. There's a minus 3a minus 6a, so it's minus 3a, and then plus 6b, because there's 8b minus 2b, so you get e to the 3 minus 6, so that's minus 3a plus 6b, and I think oh, and then there's from the c as well, so you get a plus 3a. So in the end of the day, this just gives you something that's e to the minus 3a again, right? The a's cancel, but b is minus a half a. So you just get in here e to the minus 3a dka. Right? So that's why forms are kind of nice for you. You just simplifies to this one equation.
Sorry, what does it say on the outside of that bracket?
Oh, just number.
Number and then partial.
Partial k, sorry. Okay. Partial, so number, which we don't really care about. Some partial k of e to the minus 3a dka. So the e to the minus 3a came from just counting up all these exponentials and using the fact that b is minus a half a. Okay. So that's our equation. It turns out that's enough. This is going to fix A, and it turns out that all the supergravity equations are solved. That's an exercise for you to do, if you like.
Just to understand, the equation of motion for the metric is in principle independent.
Sorry?
Just to understand, the equation of motion for the metric is in principle independent, but solving the equation of motion for C is enough to solve that?
Yeah, so there's a sort of a rule of thumb, but I don't know how what the status of when it's exactly true is that if you solve delta psi equals 0, then you only have to impose one of the equations of motion for the gauge fields. Now that's a rule of thumb. Certainly it would require things like not having a null direction. Like we saw for the PP wave that it was a bit special. There were papers on this, and I'm sure there's a more concrete answer. But, of course, when in doubt, compute everything and show it's. If you were going to publish a paper, you would, I would hope, make sure that it really solved everything. So let's rewrite this, of course, because what does this mean? Let's write that's so e to the minus 3a is h, so then you have dk h equals 0, so h is harmonic. And what does this tell us? Remember, this was e to the 2a, so e to the 2a is h to the minus 1/3. 2/3, Neil. And we had e to the 2b, so e to the 2a is therefore h to the minus 2/3. E to the 2b is e to the minus a is h to the 1/3. So that's our metric, and C012, if you look at it, it's just plus or minus h inverse. And h is a harmonic function. So we can write it as 1, because we want at infinity this thing to go to flat space. And then it can have a bunch of poles, a bunch of solutions, with some number, r to the 6 over x minus xa to the 6th power. And you're summing over various insertions. Yeah. So this is the famous M2 brane metric. So it's an M2 brane because it's extended along two directions, 1 and 2, and then time. It has a non-trivial profile in the transverse space, and actually, if you know GR, it looks like extreme rights of Nordstrom. Have you studied extreme rights of Nordstrom? And that's because it pretty much is extreme rights of Nordstrom. Extreme rights of Nordstrom is characterized by the fact that the mass is equal to the charge. And actually, that's what we're going to see here. The mass, the ADM mass of the space-time is also equal to the charge. The charge of what? Well, there's a charge, and I'm going to write 1 over the volume of the 7th sphere, integral over a 7th sphere. What's the 7th sphere? It's the sphere at infinity of this 8-dimensional space. Yeah. And then star C. C is a 3 form, so star 3, sorry, not C, G. G is a 4 form, GC. Star of that is a 7 form. So this would make sense. And this is the analog of what you have in Maxwell theory, right? That you integrate star f, which is a fancy way of saying you integrate f0r at infinity, right? This is analogous to that. In 4 dimensions, the sphere at infinity, spatial infinity, is a 2-sphere, and so you can integrate f0r of that, which is actually star of f. And this thing, well, according to my notes, but that could be wrong, is something like plus or minus 6. There's an r to the 6, and then it counts the number of poles. So some number which is can absorb times the number of sources. Yeah? So this is the M2 brane solution. I guess we should have a break. Is that? Yeah. My next thing to do, the next trick, is the M5 brane solution. I won't go through all the gory details of it like I did for this one. But it's in the notes if you want to see it. Trick, of course, because it's very famous. Right? The M2 brane metric. So of course it looks like extreme rights of Nordstrom, and when you go in near to where this H diverges, so near one of these sources, that's supposed to be going close to these M2 branes, but actually it doesn't go to a singularity, it goes to ADS4 cross S7. But I'm sort of pretending that these lectures are given before before ADS CFT existed. So it's like you'd notice that and you'd think, oh, isn't that cute? And that's what people did do. Okay, but in the interest of speeding on, that was the M2 brane solution, and it's what we would refer to as an electric solution. Just like an electron, it couples to the gauge field through the time component. There's another ansatz if you think about it. It's a little bit more obscure the first time around, and that would be an M5 brane. So one way to think about it is the following. Is if you have d star dc equals 0, okay, that's not strictly speaking true, there's a c wedge dc term, dc wedge dc, but that's 0 for us, so we will ignore it. Another solution is to say, well, let's let star dc equal dc tilde. Now if this was a 3 form, this is 3, 4, 7, So this is a 6 form. So you might imagine a solution which is very similar. But now I'm going to have C tilde not 1, 2, 3, 4, 5, not 0. So I'll do the same kind of ansatz. The only thing that really changes is the range of the indices. This is now from 6 to 10. And therefore my G, I, J, K, L, it's going to be epsilon I, J, K, L, M, dm C tilde. So this is the original G, which is star of dc. So the only thing that's different is that what I called mn went from 1 to 1, 0, 1, 2, now go 0, 1, 2 up to 5, and I, J go from 6 to 10. So there's 5 of them, and hence I've got the 5 index epsilon here.
Why are you ignoring the transients? I think this is not the equation of motion.
It's not. There's a dc wedge dc term, but for these simple solutions, dc wedge dc is 0. Why? So in the other case, if only 0, 1, 2 is not 0, yeah. And here there's simply not enough room. If you like, what I've turned on is actually C, I, J, K in this language, right? So G, I, J, K, L, the answer is epsilon I, J, K, L, M, dm C tilde. So that would what you'd be corresponding to, oh, this is a capital M, not a little m. So it's a 3-index C. Well, another way to think of it, G wedge G is 0, because it's a 4 form in 5 dimensions, so it can't. It's a very important term. I'm not saying it isn't, but it doesn't play a role in these solutions. Anyway, you can go through and do the same calculation again. You can use the same vielbeins, you just have to change the indices, yeah.
So you're saying there's a local description in terms of C?
Yeah. Yes, there is.
Okay.
Well,
it's contrary to Maxwell theory.
Well, no, it's exactly like Maxwell theory. So there's a C, but it's not globally defined. So that's what you mean.
Right, yeah, fine.
Yeah. So So it's exactly like the Dirac monopole.
Yeah, which has no local description in terms of A. Globally.
Yeah, we're mixed. I see what, yeah, I wouldn't say it like that.
You have to patch it.
You have to patch it.
Yeah, fine.
There's no global description in terms of an A,
Yeah.
but there's a local description in terms of an A.
Yeah, that's right.
Yeah, but it's exactly analogous. And in fact, before we had a lot of trouble doing the equations of motion. We had to do the equations of motion. And here, well, the equation of motion is actually automatically satisfied. If you think about it, d star g is 0 on the nose. Because the star will just remove the epsilon, and then you just get d. What is not obvious is that, in this way of writing it. So actually, it's this equation. It's not hard to see if and only if dk c tilde equals 0. So actually, c tilde equals h. And if you did the case of the multi-Taub-Natt solution, you'd find something similar. That you can write an ansatz like this, but in order to show that there would locally exist a gauge field, this has to be harmonic. So I won't go through, except it took us a while, and it's in the notes. But what I think you should find is that C tilde is minus or plus e to the minus 6a, and b is, what do I say? I must say what b is. Minus 2a. And we've already seen that C tilde has to be the harmonic function, and the spinor is, according to my notes, it's e to the minus a half a epsilon 0, and gamma 6, 7, 8, 9, 10. I did it this way. Epsilon naught is plus or minus epsilon naught. Or you can swap this. I did 6, 7, 8, 9, 10. But because of 11 dimensions, the product of all the gammas is 1. So you could also write this as gamma 0, 1, 2, 3, 4, 5. Epsilon is epsilon naught. But in my notes, I did it like that. So that's the solution you get. And the effect is just quite similar. This becomes h to the minus 1/3, and this then becomes h to the 2/3, if I'm not mistaken. Yeah. And actually then there's a plus or minus here. So that's the solution that you get for an M5 brane. It's in the notes. I'm not going to go through you saw how kind of laborious it is, and but if you'd like to see it, it's in the notes. Okay. So that's the M5 brane solution. Okay. So the next topic I wanted to do, by the way, it's called a magnetic solution, which we'll come back to later, because what's the charge here? The charge would be 1 over the volume of a force sphere times the integral of the force sphere of just g. And the force sphere is the force sphere at infinity of this transverse 5-dimensional space. So that's the charge. And this, I claim, is something like plus or minus 3 r cubed, where that's some scale, times the number of sources. Okay, so now I want to do something that's very important but not often talked about. Non-perturbative stability. And actually it's classical stability. Yeah.
Just about this still, like at this stage, is there anything that one can see about the relationship between M2 and M5 branes and like the world volume theories that people then end up studying? Or do you need multiple of them to even?
So there are multiple of them, because that's what this harmonic function has poles, and you can imagine them all sitting on top of each other. That's what one usually does. So actually you usually take H. If they all sit on top of each other, then they become something like n. And for the M5 brane, it's m over r cubed, where r, because they're all now at the origin, they're not sitting out wherever you want. But they can sit wherever they want, which is rather remarkable. How is it that you can put black holes and they can be stable and they're not like eating each other up? And the answer is because there's something akin to electrostatic repulsion that exactly balances the gravitational attraction, because both have a 1 over r. In 4 dimensions, both have a 1 over r squared law. So that would tell you that there's a moduli space of where you put your branes. Then you take, but if you put them all on top of each other, and then you can take the so-called near horizon limit, where r is small, little r is small, or capital N is big. You drop the 1, and then these solutions become ADS, cross spheres. And then ADS CFT kicks in, and you say that that's dual to whatever the gauge theory is that controls the branes. And that gauge theory has a moduli space, which is the moduli space of n indistinguishable particles in 5 dimensions, or 8 dimensions within 2 branes. So you have to find a gauge theory in 5 plus 6 dimensions for the M5 branes, whose interacting gauge theory, whose moduli space is the symmetric product of R5, n copies of R5. and has 16 supersymmetries, because that's plus conformal symmetries, and that's not known. And then for the M2 brane case, you'd need to find a three-dimensional conformal field theory whose world volume has a moduli space, so the symmetric product of n objects in R8 and 16 supersymmetries. That is known. It's BLG or ABJM. But the 5-brane case remains one of the most mysterious things in theoretical physics. So you can read off some aspects, and of course you can do more fancy stuff than this. In ADS-CFT, you can read off the entropy, for example, and you see that it goes like n to the n cubed in this case, and n to the 3/2 for the M2s. So those are things you can read off from ADS-CFT. I mean, by now there's quite a lot. You can read off some correlation functions.
But this is from ADS-CFT, not from like brain engineering or something?
No. So my moral when I prepared these lectures was not to pretend that we didn't quite know ADS-CFT yet. So I just as a game that we don't go there. What could you know without ADS-CFT? You could look at these solutions and you'd realize that there was a moduli space of solutions of these black holes. And you could compute the motion of the moduli space, the slow motion approximation to black holes moving. It turns out it's like a free theory at lowest derivative order. So these are just freely moving objects. What else could you know? At this stage, not much. Maybe we'll revisit that a little bit, because this is M theory. You can, actually, there's a nice paper which shows how you can construct the effective field theory, at least the modes of the effective field theory, by looking at the Goldstone modes. So these solutions break symmetries, global symmetries, so they have Goldstone modes. And rather peculiarly, the M5 brane is known to have a Goldstone mode which is a self-dual 3-form. And you can see that from supergravity, plus scalar fields from their positions.
Which global symmetry?
It's a bit more complicated, so you have to, well, they did it from supersymmetry. Yeah, and there's a form field. So you can look at large gauge transformations of this thing, that so-called large things that they don't die off at infinity, and that'll give you some weird 3-form gauge symmetry on the brane.
But it's not just partitioning 11 dimensions into, that's not the global, it's not 11-dimensional like Poincare invariance that's being broken and leading to this Goldstone boson.
So some of it's that. So let's take the M5. M5. So what do? You had R110, and it's broken to R15 cross R5. SO110 goes to SO15 cross SO5. This leads to what's called an R symmetry. So you need a symmetry where you have an SO5. This leads to world volume Lorentz symmetry, Poincare symmetry. This breaking leads to Goldstone modes, which are translations. You've also broken translations because you picked an origin. So you broke translations. So. So you've broken translations in the 5-dimensional transverse space, so that would give you 5 scalars. 5 scalars. And they are in an SO5 of the R symmetry. Now, supersymmetry tells you that 5 is not good. There has to be more degrees of freedom to get a supersymmetric multiplet. And if you had a gauge field, A mu, in 6 dimensions, that would have 4 degrees of freedom. And 5 plus 4 is 9. Also not good. So supersymmetry alone tells you have to add something with only 3 degrees of freedom. And the answer is a self-dual 3-form, which is usually called H. It's got nothing to do with that harmonic form. Well, let me just not call it that one. Let me say dB equals star dB, and this is a 2-form. That guy has 3 degrees of freedom. But there is, you can argue it from looking at Goldstones in the field theory. And if I did the M2, a little simpler. It's R110 goes to R12 cross R8. Oh, I just get 8 scalars, and that's good. And an SO8, SO12 cross SO8. That's a good supermultiplet. Although it turns out, you add fermions, you also have to add the gauge field. Even though the gauge field in 3 dimensions is not dynamical, it has a Chern-Simons kinetic term. So it doesn't add local degrees of freedom, but it's important for the theory. So this is altogether, in some sense, a simpler beast than this one.
Is there a Goldstino for the broken supersymmetry?
Yeah, that's what the fermions come from. So all the modes in the abelian theory, certainly all the fields have an interpretation as coming from Gold's breaking of some symmetry. Yeah. Okay. Right. So you might well be familiar with the BPS arguments for why a charge mass is always bounded below by charge, and hence a state which has charge equal to mass is going to be absolutely stable, can't decay, and this is related to supersymmetry. But I think it's, as I said, it's somewhat forgotten, but I think it's an important part is to see how this works non-perturbatively in the gravity theory. And these proofs are all based off a proof by Witten of the positive mass theorem way back, like 1980 or so. And it's been streamlined a bit, so what you do is you introduce a so-called Nestor tensor. And the Nestor tensor, and I'm going to try to be general as possible, is a 2-index tensor. And you construct it like that. And by the way, now we're doing sort of math, spinorial math. The epsilons are going to be commuting spinors. I'm allowed to do that. They just are. This is just geometry now. What is the point of this thing? What does it do? It satisfies that d mu e mu nu is delta psi mu bar gamma mu nu lambda delta psi lambda, and then in principle there could be another term, but some other spinor. That's what you want this thing to satisfy on shell. So this is a classical statement. So when you use the equations of motion, you want that d mu e mu nu is roughly speaking like the square of the supersymmetry variation, plus maybe another term. I'm not going to talk about this other term. I'm just saying it can be there in some dimensions. We don't need it in 11. So we will ignore that for now. Well, for the rest. To show this to supergravity is a bit painful, because remember our roughly speak, I'm just being very schematic. Yeah. That's our thing. So obviously, when you put this in here, you compute this. You're going to get terms over here which are linear in G and quadratic in G. The linear in G terms go away on shell. Well, and the quadratic ones, they go. Sorry, the linear ones just vanish, and the quadratic ones go away on shell because they're related by the Einstein equation to the Einstein equation to r mu nu minus 1/2 g mu nu r, which I'll show you in a second. So what I will show you is at least one thing. Let's look at pure supergravity, right? So I'm going to spare you the grief of showing this. I spared myself the grief of showing it in my notes. You'd have to whack that in here, and you would see that's true. Chi is 0, I believe, in this case. Yeah. So this turns out to be true on shell. If I take 11-dimensional supergravity, and I take this tensor, and I take d mu e mu nu of it, I'm going to get this. So to convince you why this is not crazy, I'll at least do it for pure gravity. And then this at least will knock off Witten's proof of positive mass and pure energy, pure gravity. So how does it work in pure gravity? So this is part of that calculation. So E mu nu is epsilon bar gamma mu nu lambda d lambda epsilon. Right? Because that's all delta psi is. D mu E mu nu is d mu epsilon bar gamma mu nu lambda d lambda epsilon. That's looking good. That's what we want. But then there's another term. D mu d lambda epsilon. So this is indeed delta psi mu bar gamma mu nu lambda delta psi lambda. The second term, well, there's going to be a 1/8 actually, epsilon bar gamma mu nu lambda r mu lambda rho sigma gamma rho sigma epsilon, right? Because it's anti-commuting the two indices. Yeah? But do you remember? We did this. G. And this was indeed proportional to the Einstein equation. So it is indeed 0 on shell. Okay. So that's how it works for pure gravity, at least. This thing, the Nestor tensor, satisfies the magical property that on shell, d mu e mu nu is this. Right? Why is that useful? Well, let's look at spatial surfaces. So codimension 2 surfaces. We're going to go out to, we're going to take a spatial slice. So that's codimension 1, and then we're going to go out to infinity on it. So that's codimension 2. Well, on a spatial slice, d mu, e mu nu, and then I would have a ds nu. Right? This is some spatial slice. So that means that I would write this as di e I 0 and then ds0, right? Because the normal vector to the spatial slice is a time-like thing. So now I can use that on shell, this becomes delta psi I gamma I naught j delta psi j. And if I had an extra chi term, you would just add it in. Yeah? So let's just do a little massaging. This becomes delta psi I transpose. There's a gamma 0 here. In my conventions, there's a gamma 0 downstairs. Sorry, it's upstairs, so it's going to anticommute through and square off. So actually, I just get gamma I j delta psi j. ds0. And then I can write this as gamma I delta psi I. Well, let me do one more step in between. All right, this is gamma I, gamma j minus delta ij. Delta psi j ds0. Now I'm wondering about my signs. Hold on. Yeah, I want a minus sign, so I'm going to do that. Okay. Yeah, that's good. And this is a transpose. This is just because there's a gamma 0 here, and well, it anticommutes through, and then squares to minus, and it's downstairs, so it just kills off the 0 component. And by the way, well, no, this is, yeah, so that's good. All good. Okay, let's rewrite this then. This is delta psi I transpose delta psi I, and then minus gamma I delta psi I transpose gamma j delta psi j. The first term is positive definite. We're now looking at just spinorial geometry. We're not looking at fermions, we're just looking at spinors on a manifold. The first term is positive definite. The second term is negative definite. But the key ingredient in this Witten positive mass theorem is that, yeah, the second term might be positive, sorry. The second term might be negative definite, but you can set it to 0. So the claim you can find an epsilon such that gamma I delta psi I equals 0. This is like a Dirac equation. Yeah? So this is just a Dirac equation, and for suitable boundary conditions with epsilon going to a constant at infinity, so if we're given any solution to the equations of motion, well, not even, any background, you can find an epsilon which satisfies that equals 0. Yeah? It's not like what we were trying to do before, which was to set delta psi I equal to 0 for every I. This is just a Dirac-like equation, and it'll just give us, you know, some equation to solve on the spatial sections, and we can solve it. Yeah? Then this is positive definite for spatial slices. So, yeah. So that tells us then that if I had some integral over the sphere at infinity of my spatial slice, that is integral over the spatial slice is positive. Right? So this is my bound. I've assumed a certain epsilon, but now I don't even all I have to know is that it exists, because this is an integral over the sphere at infinity, where epsilon is constant. So all I have to know is that there exists an epsilon in the bulk, in the whole of the spatial slice, which satisfies this equation such that it's constant at infinity, and then I know that this integral is positive. But this integral knows nothing about what goes on in the middle. right? So the question is, what does this give us? So we have a bound. So what is it? Now when I say it's a bound that no classical process will violate, right? Because I've assumed that the equations of motion are being satisfied. It's not a quantum bound, it's a classical statement. There is no solution to the equations of motion that can make this negative. Okay. So what we're after is, in particular, we have integral over some spatial sphere at infinity of epsilon infinity, I call it, and I've changed it, well, the ordering. All right. So that's what I have. Sorry. So there are various terms in here, of course. So for M theory, it's this. Is it okay if I use this notation? The bar just means I'm contracting by whatever's left. Yeah. So we just have to look at what each of these things contributes to the integral. So the first one is this. So what do we do? Remember now, we're at spatial infinity on a space-like surface. Yeah. That's what this integral's over. It's not in the bulk, it's at infinity. And it's only spatial. So we can take the metric to be flat plus a correction suitably vanishing at infinity. Which means the vielbeins are just flat plus, and then a slight, well, not an abusive notation, but this. So H is going to 0, right? And as for the spinors or the gamma matrices, they're just the flat space gamma matrices to lowest order. And epsilon is epsilon infinity plus ... Okay, so we have to work out what the first term, the gravity bit, is. What do we have? We have epsilon bar infinity here. R is the radial direction, so I'm going to assume that at infinity we have spherical symmetry to leading order. Yeah? And I'm just going out in the radial direction. So this is what I have to evaluate. And that is, of course, I epsilon bar infinity 0 R. And then it's d, 0 R here. dj epsilon plus 1/4 omega j, and then in principle there's mu nu gamma epsilon, and then I should put the bars, but I'm going to drop the bars because remember everything's at spatial infinity. So the gamma matrices are the flat, the space, there's just the flat gamma matrices. And I'm not going to put bars, underlines, just to save writing. It turns out this term is subleading. It's a little not so obvious to see that. Spherical symmetry is going to give it to you. So then you're just left with something like this. There's no I. I don't know why, but the I. Habit. And notes. 1/4 epsilon at infinity. So then I'm just left with this. And I'm not putting the underlines. Okay. This, again, at leading order, I'll call that K, and then it's xk over R. That's just, what the gamma matrix the gamma R matrix looks like. It's xk over R times gamma k. And then here, well, what do I use in my MN? I'm going to assume that the time-like things drop off too faster. That's just for simplicity. It does for a static solution. Of course, you can take your favorite solution and boost it, and then these terms will not be zero, not be subleading. The time-like terms where there's a zero here. So MN are spatial. But for simplicity, I'm going to assume that it's static at infinity, stationary. Yeah. This can be done more generally. Static is stronger than stationary. Static at infinity. So the omega I nu whatever is zero, subleading. Okay. So this is what we have to work out. Well, for once in my life, I use that formula that I said I never found useful for what omega is. Okay? And do you remember it off by heart? Probably not. Okay. I'll write it out for you. Well, it had G's in it. Well, it had E's in it. And E inverses and such. And these are the E's. There's a delta and then a half H. So obviously, if I take a derivative of delta, I get 0. So the derivative only sees the H. So this is this formula I have before. And that gives the leading order behavior is when the derivative hits the H. And hence, the E's. Do you remember? Well, let me write down the formula roughly, right? Schematically. Schematically, it was something like... There's a 2, and it was things like the following. E inverse dE minus E inverse E dE. With indices sprinkled about and anti-symmetrized in nasty ways. But the point is that when I write this out in this expansion on the right, this is just going to look like delta dH minus delta delta dH. Schematically, right? At leading order. And what it looks like in full glory is the following. L, M, DJ, H, L. Anti-symmetrized here. And anti-symmetrized. So it's anti-symmetrized always on M and N. And then minus 1/2 delta L M delta N S anti-symmetrized on MN, and then delta J T H S T. That's what we get. Remember, the half shows up because H has got a half in it. So this is some nasty expression. And then, of course, I've got the other thing, which is this epsilon bar infinity gamma naught kj gamma mn. I've raised the index, but that's fine. Well, the gamma naught strip off, so this actually just becomes epsilon transpose gamma kj gamma mn. And so you get this kind of gamma matrix expansion. So gamma kjmn, and then there's going to be a bunch of terms where you have a 2 gamma and a delta. And then there's a term where you have no gammas, just delta delta. Is that, do you know what I mean? When I write gamma kj, we've done this before, that's why, of course, you know, so you're totally on top of it because we did it before. This is gamma, a 2 gamma times a 2 gamma. It's a 4 gamma plus a bunch of contractions times 2 gammas plus a bunch of different contractions times no gammas. Yeah? So that's what we find. This guy will give 0 because he's totally antisymmetric, and eventually you'll find something symmetric in here. Yeah. Sorry, I'm missing a derivative here, by the way. dl. So this guy will not contribute. It turns out the second guy also does not contribute. It's a little harder to see. The reason is spherical symmetry. At infinity, this will always look like xx times something, times an h prime or something. The only thing that you have with an index is xi, xj. Yeah? If you expand this out, everything's going to be, any free index has to be proportional to, if any free I index has to be proportional to xi. Yeah? So this also kills off this, because there might be terms, but they're going to have things like xi, xj times gamma ij. Oh, that's 0. Because of spherical symmetry, there's nothing else. So these terms also go away. I mean, sit down and think about it. So you're just left with the various contraction terms. What are they? Well, at the end of the day, they're just deltas, and there's only 2 ways you can do it. So what you find is sorry, not dr. D. So this is the thing that we're looking at, and this we convinced ourselves, well, there's a half that comes from just the, well, let me write it out. There are no gammas, so I just pull this out. Right? So this has killed all the gammas that sit in this horrible expression, and there's an x out here, and, right? There was a quarter, but if you do the adding right, you get a half. Well, actually the quarter comes back. Let me just pull this out. And then you get the xk over r. In fact, it's over 2r. So that's this bit here. And you get a factor of 2 from when you expand out this mess and collect like terms and the factors of 2 that appear here. You don't want me to be more detailed, right? It's in the notes. So you can follow. And then you get this rather nice expression. It's dkHmm minus dmHmk. And then, of course, there would be integral over d minus 2 directions in general. Okay, that's what you get for the first term. Has anyone seen that before? That's the ADM mass. It's actually 1/2 That's rather beautiful that it just follows out of spinorial geometry. Supergravity. More generally, I assumed it was static at infinity. If you did boost it, you'd get a combination of ADM mass and ADM momentum. So this would be something like p mu k mu. Sorry, p mu, v mu, let's say, where p mu is the momentum of the space-time, and v mu is however you boosted it. Okay. So the only thing remains is to, and I do it in detail in the notes, but I'm not going to go through how you contract all the indices like I painfully did for you earlier. What you find is, it's not too surprising, of course. You have this thing. So let's do M2s. What I told you here is true for any supergravity in any dimension. So if I do my M2s, so that meant that C012 was not 0, or more precisely, G012I. Now, we forget the 1-2 directions. They're infinite, they're not playing any role. So what we're actually computing in that case is the mass per unit area in the 1-2 directions, because just nothing's going to happen. So then, this thing, well, it shouldn't surprise you, I hope. If you work it all out and use the word, you actually get plus or minus 1/2 epsilon transpose epsilon infinity times G012R. So it's a bunch of steps. That's the only thing it could possibly be. You have to trust me on the half. And I don't trust myself on the half, but it looked good when I got it, so I left it. You know, it's like when you write a paper and you keep looking for mistakes, and when you've got the answer you want, you stop looking for mistakes. Well, that's how these notes are constructed. And of course, at infinity, G12R is just xk over r times G012k. That's all I mean. And if you did the M5, that mess, again, gives you plus or minus 1/2 epsilon transpose infinity, epsilon infinity, and then what it gives you is dr of the C tilde that I mentioned, which is the dual. So again, these integrals are giving you what I could find as the M2 brane charge and the M5 brane charge. And so the bound is that the ADM mass is greater than charges. Now, of course, you can't really do, or you can, it's more subtle, you can't really do both at the same time, because one's got an 8-dimensional space and one's a 5-dimensional space. So it's one or the other, at least in the simplest cases. And so the argument is that this bound is satisfied by any classical process in the theory. And in particular, it shows that if you forget the M2 branes, what I've shown almost explicitly, it's in the notes explicitly, pure gravity. Pure gravity, the ADM mass, is positive. It cannot become negative by any classical process. There is hidden assumptions. The hidden assumption, of course, was the solution to this Dirac-like equation, so that means there has to be a smooth space-like surface to start off with. You could certainly start with negative mass Schwarzschild and violate this bound. But then you have a problem with solving this di epsilon equals 0 thing. As long as you can solve that smoothly over the whole space-time at some initial time, then this mass must be positive, it can never become negative. But more generally, it's bounded by the charges. How this works specifically is a bit fidgety by dimension, but you can, it's all, for all the solutions you'll ever encounter, someone has done this argument and shown what the charges are and what the exact coefficients are, which obviously I've been a bit funny with. Yeah?